So how's PA2?
Done.
Done. Are you, if you're not done, are you feeling generally like you know how to get there, or is it kind of like there's this big thing you have to get through and you're not sure how to do that? You're not sure like what the next step is or things like that? Do we want to talk about sort of like how to get from here to there? The reason I ask is that the assignments in this course are bigger than they were in 222, 224 in a lot of ways. And we don't have ODPs. The ODPs were ways to sort of like compel you to do the pieces of your larger programs in steps leading up to it. But when you go on to a university or in the workplace, right, typically you're going to get these large programming assignments where the specification, for a university course might be 10 or 20 pages. The specification for something on the job might be 100 or 200 pages, right? And taking that and figuring out, what's the first line of code that I write is kind of a really daunting thing in some ways, because you're going to say class something curly bracket, right? But what happens after that? And so part of what you're getting practice with in this course and will in other courses is this process of taking a large problem and somehow being able to understand the whole thing and then figuring out how to break it into pieces and pursue each of those pieces in a reasonable way. So this is where things like Modular Ization comes into play. This is where being able to test each piece along the way becomes valuable. Writing test code to test this section that you've been working on. These are all skills that lend themselves well to tackling very large projects. And Java in particular is a really well-suited way to do that kind of compartmentalization because we have this idea of objects and classes. So that to do a word list you need to have a list of integers showing the location of each word. And you could do that with an array if you believe there's a maximum size. You could do it with a linked list, right? So if you start off and you're trying to write your word class and you get to the point where you need to have your linked list of integers and you start writing code for that, right, then you kind of have a C-type experience where you just have code that gets longer and longer and indents more and more variables, and it becomes more confusing the longer it is. If you think in the idea of objects, right, it doesn't necessarily get more complex, even though the problem is more complex, because at some point you say, okay, so here's my word list. I need a list of integers. I'm just going to call that, integer list or location list for us. And you decide, what does a location list or an integer list entail, right? I want a linked list of integers. And you make yourself a Christmas list, right? A wish list. So what do I want to be able to do with this? Well, I want to be able to add something to the end of it. Okay, so I'll have an add number to end of the list method. And I'd like to be able to print them out with commas in between. Okay, so I'll have a print with commas in between method. And all this stuff that you want to do with this object, this linked list, you just sort of like say, I'm going to make a method for this and this and that. And you specify what those things take in, what they do, what they give back, and you just assume that you're going to have this class, location list or integer list or whatever you call it, and then you use it. So in your word list, you're not writing code for a linked list. You're saying, okay, so I'm just going to have a linked list here, and I'm just going to call its, print with commas method. And you can do that first, or you can decide what you're going to want in your linked list. You can abandon your word class for a while and write your linked list class. But at some point, you're actually writing the code that makes a linked list, and when you're doing that, you're not thinking about the word list. You're not dealing with scanners and parsing in lowercase. You're just building an integer list. and you write test code and you check out all the methods and make sure they work, and you debug it and you convince yourself that that's correct, right? And then you go back and you use it in your Word class. So figuring out where to make these divisions is a big part of the challenge. And I usually recommend that particularly with larger programs, before you start writing any code, you figure out what your data structures are, what your classes are. What are the pieces of this that you want? So what is an index utility going to do? Well, that's specified in the assignment. And the build index utility, that's specified what that should do. But at some point, it starts to become less strictly defined, and you can start to say, okay, I want a linked list of integers. So I don't care if it has a sentinel or not. When I'm using the linked list, here's what I want to do. I want to construct it, I want to add things to it, I want to search for something in it, I want to print something from it, whatever, right? And this is the abstract data type idea again, right? Think about what you want to do with a word list. Design that interface. What are the methods I'm going to call to do these things with the word list? And then use those to define whatever it is that's using the word list, in this case index utility, the build index method. But the more you can have that separation, right, the smaller the pieces that you have to work on. And that's one of the goals here, is to get better at making that separation and doing that piecewise development. So any questions I can help you with on this? Okay, proceed confidently. All right. I've been saying we're going to talk about graphics, so let's talk about graphics today. I made another update to PA2 assignment, and let me just mention it here. In the description of the assignment, it says that you should print the list of locations as a space-separated list. In the example output, it shows a comma-separated list. You can do either, okay, since I was ambiguous in the write-up. Spaces or commas, either way is fine. And I put that in the posting of the PA2. That's not a trick. Okay. All right. Let's talk about graphics. So I'm sticking with IntelliJ for now. I went through a big existential angst over the weekend about IDEs, and I ended up coming back to IntelliJ because for various reasons. So we're going to keep using IntelliJ. Even though it's a little slow to start. So I'm just going to make a simple dialog. Remember, we're going to do new dialog when we want to do something with widgets and other GUI components. I'm going to take off these OK and cancel handlers, and I'm just calling this main. And if we run this, not a whole lot happens. We get a window over here.
With OK and cancel.
With OK and cancel. Bless you. Which don't do anything because I got rid of the code, but the buttons are still there. But it's just an empty window, right? But there's a lot of stuff going on. So it's got the OK and cancel buttons, which we're going to get rid of. It's got a picture of the little happy animated coffee cup symbol up here on the left, which is really hard to see. It's got the maximize button, the close button. When I hit the corner, my cursor changes, and I can drag to change the size of the window. When I hit the top bar, my arrow gets big. If I right click, I have options for manipulating the window.
Which is itself its own miniature text box.
Yeah, yeah. And if I click here and drag, my cursor changes, and there's all this stuff going on, right? And I haven't written any code to do any of this. This is the entire class. Right, so some declarations, constructing my main method says set content pane, set modal true, and set default button. And my main method constructs a main, calls pack and set visible, and exits. So there's not a whole lot going on here, but there's not a whole lot of code here, but there's a lot going on. So let me get rid of these things. So even like this, if I run this, you get a little tiny window up here, and it's got all that stuff. All right, so we want to do something like draw a line or draw a rectangle on here. Okay, that's our immediate goal for the afternoon. Make this so that when we run it, there's a rectangle that appears in the middle. So let's talk first of all about where rectangles come from. If you have a window or the front of your laptop or something, and we want to draw a rectangle right here, how does that happen? How did that rectangle just appear on the screen coming from that projector? So how many people remember TV sets with cathode ray tubes? These were cool because they were big, right? And they were dangerous. They had several hundred toxic compounds inside them. And you would put your kid in front of it, you know, to entertain them. If the tube ever shattered, it was a major disaster. It'd be glass flying everywhere and toxic compounds coming out. So amazing devices. And they contain a thing called a cathode ray tube. And so here's a sample picture of a cathode ray tube. This is, you know, they used to be these big glass things, maybe this big. The bigger the picture, the longer the tube. Okay, so it was roughly cube shaped in total volume. And so this end over here would be much taller and very wide. And inside there's a piece of metal basically that gets really, really hot. And when you heat up metal, it spits out electrons. Okay, so this is something called a cathode. And so these things took a lot of power, right? Early TVs, no way you could have a battery-powered one or a portable one. It had to go into the mains in the wall. So the cathode gets hot and spits out electrons. And you have this thing called a grid, which is a way to focus the beam of electrons coming out so they come out in a straight line. Or if you put the right kind of charge on this grid, you can stop the electrons from flowing through. Electrons are negatively charged. If you put a negative charge on the grid, the electrons are repelled and they stop coming out the other end. Otherwise, they travel through. And there's some more electronics here that accelerate the electrons, gets them moving faster. But the interesting part for us is this vertical deflection plate and this horizontal deflection plate. So vertical deflection plate, it's a pair of metal plates, and by controlling the current on those plates correctly, this beam, which is negatively charged, may go straight or it may bend up or down. And so if you take that beam that's normally going straight, so picture a garden hose hitting the middle of the wall in the back there, if I deflect the beam up, now it's hitting a spot higher up. If I deflect the beam down, it's hitting a spot lower down. And as it leaves that deflection, it goes through this horizontal deflection plate, which can take the beam and further deflect it left or right. So if I want to hit the spot right over there on the wall with this beam of water or electrons, right, I deflect it up a little bit and I deflect it over the right amount, and now it's hitting that spot. All right, so the end of this tube is covered with a material that lights up when it gets hit by high energy electrons. It'll glow. So electron beam, very small, hits this spot of phosphor on the inside of this glass and it lights up. And when the beam stops, it stops being lit up. But it takes a little while to stop. And your brain-eye combo sees this as a spot of light on the display. And so that's the basic mechanism. Now this doesn't happen in, you know, an LCD panel or a flat screen TV or any modern device that's been built for decades. But the principle is still useful for understanding how we control this, this display. So that's what old TVs looked like, right? So that's a big vacuum and bunch of coils of wire back here to produce these very powerful magnets. And this is the end that plugs in, and lots of good electronics in here. And this is a fairly modern looking TV. So the older ones, you know, they would have tubes in the back instead of transistors. And so you turn it on and it takes a minute to actually start up. And when you turn it off, it takes a few seconds for the thing to actually go blank. And people still use these things for like hobbyist experiments. So. All right, well, how do we use this movable beam to draw pictures? We could just point the beam here, move it across, come down, move across, go up, and keep doing that, and that would draw a rectangle. It would be a really beautiful rectangle. And there are some systems that work like that. They're called vector displays. And if you want to draw a circle, you basically put the beam right here, turn it on, and then you change the horizontal and vertical deflection simultaneously in such a way that the beam moves in the shape of a circle. And you get a beautiful circle. You know how if you look at a circle up close on a typical display, it actually looks kind of like this? Right? That doesn't happen on a vector display. All you got to do is put in a sine wave for the horizontal deflection and a cosine wave for the vertical. And if you do the equations, it'll move in a circle. And there's no rasterizing. That's what this effect is called. Right? But it's a fairly cumbersome device to control, and there's no really good way to sort of transmit the information for what you want to display. If, you know, here I've got to use a square wave, and here I got to use some sine waves and so on like that. So the way that TV works, right, because the goal is to be able to broadcast things and pick up images, the way that TV works is you start scanning. You put the beam up here in the upper left, and you move it from left to right. And you sweep out that top line of the TV display. And then when you get over here, you bring it back over to the left, but you turn it off first. And then you move it down a little bit, and then you sweep over again. And then you turn it off and fly back, and move down a bit and sweep over again. And you keep doing this until you've swept out the lowest line, and then you turn it off, and you come all the way back up here to the upper left, and you do this again.
That happens incredibly fast.
That happens 30, 60 times a second. So when you look at the frame rate, right, that's how many times it's doing this entire process. And you got to do that, I think, like 12 or 15 times a second for motion to look like smooth motion to your brain. But the faster, the better in some ways. And again, obviously, there's no electron beam sweeping inside, you know, my laptop display. But this is still the model that's used. For example, if you use a VGA cable, right, to connect to a display like that, what do you send down that VGA cable? What sort of signals? It looks something like this. So there's a blank spot in the beginning where the CRT is off, and then there's so the horizontal sync says move back to the left, right? And then start displaying each pixel that you want, right? Turn the beam on and off at the right spots. and when you get to the end, go back to the beginning again. And that all represents one line of the display. So draw a line, draw the next line, draw the next line, and so on. When you're done, turn off your beam and go back to the upper left corner. And so on a VGA cable, there's pins to say should the beam be on or off. There's pins to say do a horizontal sync. There's pins to say do a vertical sync. And you basically generate waveforms like this, and it moves this imaginary beam. Well, it displays what you would get if you were moving this imaginary beam in this way. And then the trick for drawing, of course, is just turning the beam on and off in the right spot. So if you want to draw this rectangle, beam off, beam off, beam off, beam off, beam off, all the way over to here. When the beam gets here, turn it on, and leave it on until it gets here, turn it off. Come down to the next line, off, 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 off. When it gets here, turn it on, and then turn it off. Until it gets here, turn it on again, turn it off, and so on. And then when you get to this bottom point, turn it on, leave it on through all of this, turn it off, and leave it off everywhere else. There's your rectangle. And so on an actual CRT, you have pixelation, right? You have old days 525 lines from top to bottom. And so this is not a solid line going up and down. It's a dot and a dot and a dot, right? 1/525th of however big your display was. But to your brain, it looks like a solid line if the dots are big enough and the screen is small enough. Okay, so this is still what's going on. This final presentation is still what goes on with, say, an HDMI or 4K display or any of this modern stuff. We basically have a display area, and you can think of it as broken into a grid in X and Y. And so each of these squares, pixels, right, can be turned on or off. And so if we want our rectangle, we might draw a rectangle by turning on those pixels, leaving everything else off. And whether you have an LCD panel, a plasma display, a projector, an old CRT, VR goggles, right? The way that we interface with it is we basically say which pixels to turn on or off. And so this is kind of like what we have with abstract data types. We don't have to change our code based on what this is being displayed on. If I write Java code that draws a rectangle on my screen and then I plug in a projector, I don't want to have to rewrite my Java code, right? So the hardware should handle that because the way I'm interacting with the hardware is through this standardized interface. So we're going to talk about this interface, and for Java we're going to use a class called graphics. And graphics is built on top of something called AWT, the Abstract Windowing Toolkit. And the connection between this abstract notion of pixels and the actual hardware that's handled by the Java virtual machine and the drivers underneath it, and the display driver, and so on and so forth. All right, the other thing is color. So I've been talking about turning pixels on or off. That's for basically a black and white display. But of course we have colors. So instead of just saying this should be on or off, we can specify.
Each pixel has a data type, like a node.
Each pixel has a data type like a node. And part of what's in that data type is how much red, how much green, how much blue that pixel should have. So we imagine 3 electron beams, red, green, and blue, and we can turn each one on or off to a varying degree. Typically each of these 256 levels. So 0 through 255 for the amount of red, green, and blue. And with light, those are your primary colors. With pigment, it's red, yellow, blue. But for light, it's red, green, blue. And different combinations of those give you different colors. So if you mix red and green, you get yellow. If you mix red and blue, you get purple. and so on. And the amount of each one tells you what the color is. So 8 bits for red, green, and blue each, that's a total of 24 bits. So old graphics cards, when they say something like 16 million colors, that's where that's coming from. 24 bits, 2 to the 24th, 16 million. And hardware will handle more than that, but this is the model we mostly encounter in Java. So 8 bits for each of the 3 guns, red, green, blue. All right, so how do we use this? So there's a class called Graphics, which is part of the Abstract Windowing Toolkit, so Java AWT Graphics. And there's a bunch of methods in the graphics class for doing all kinds of different types of drawing. So for example, if we want to clear a rectangular area, fill it in with a background color, we can call the clear rectangle method. And we give it an XY coordinates for the lower left corner and then width and height. Well, let me talk about coordinates really briefly, because this is a little weird. So suppose your display is 1024 by 768. So this is X going horizontally, Y goes vertically, but 0, 0 is always in the upper left, which is backwards from math class. So this point down here would be 1023, 767. All right, so we can clear rectangles, we can copy the areas contained inside a rectangle, we can draw 3D rectangles, which aren't really 3D, it just adds an outline to make it look like it's got depth to it. We can draw a circular arc, right? XY position of the center, I believe, width and the height, the 2 radii, because it's thinking ellipse, and then a starting angle and the angle of the arc. We can draw characters, because if we want to display on our screen ABC, right, those are just shapes. It's not like a terminal that has built-in hardware so that if you say, you know, here's ASCII character code 65, it displays an A. That's got to be done, that mapping from I want an A to light up these pixels that look like a triangle with a line going across the middle, right, that's got to happen somewhere. So the draw characters method will do that for you. We can draw image, so we can read in something like a JPEG file or a PNG or some other graphics image, and we can display that directly using these various draw image methods. And there's a bunch of those. We can draw lines. Well, how do we draw lines? Suppose I want to draw a line. We did a horizontal line and a vertical line, but suppose we want to draw a line from this point to that point. Which pixel should I light up?
The one closest to the 0, 0 point?
Well, I'm going from here to here, so I want this to be what displays. But if I've got to specify XY values for pixels to turn on, well, I know, let's say this is 1050, and let's say this is 25. That's not drawn to scale. Right? Well, I know I want to turn on pixel 10, 50, but what's the next pixel I should turn on? Probably 11, something slightly less than 50, right? And probably 12, something even smaller than that, in such a way that when I get over to x equals 20, I'm lighting up pixel at y equals 5, right? But you've got to do this calculation somewhere. So this is called scan conversion, and there's lots of algorithms for doing scan conversion. Bressenham scan conversion is a classic. That's usually handled by hardware. Or maybe not. Maybe your graphics card is from the 70s and doesn't do this, and there's a software loop that's figuring out which pixels, right? But to us, that doesn't matter. We're just going to say, draw a line. We're going to say starting XY location, ending XY location, and a line's going to get drawn. Okay, so this is serious, like, layering of responsibilities.
Could it be that the program also does this internally, like an object?
Which program?
The draw line method.
Yes. So, and someone from the earlier section looked it up, and it claims that if you have a GPU, Java won't use it, which is kind of shockingly hard to believe, that there's no way to take advantage of your graphics hardware. So I don't know to what degree that's true. But something ultimately, when you call draw a line, is deciding which pixels get lit up. Here's another thing. Because we have this grid of pixels, right? If I try to draw a line from here to a point just slightly higher, what's going to actually happen? It's going to end up looking like this. And on older displays, especially if you had lines that were almost horizontal or vertical, they got this really jagged look, and it was really obvious. And so there's tricks you can use. This is called rasterizing, right? This undesirable effect. And there's tricks you can do, like when you have this horizontal vertical leap, color a few pixels nearby. Not quite as dark as the line itself, but basically blur this, right? So make it a bit of a blurry line in such a way that when your brain interprets what it's seeing, it says, oh, that's a nice smooth line, right? So that's anti-aliasing, trying to undo this aliasing effect. And that can be done in hardware, it can be done in software, it can be turned off, right? And we don't have to worry about it when we're in Java and we're saying draw a line, right? Whatever the anti-aliasing policy is that's set up, that's what's going to happen. So we can draw polygons, we can draw rectangles with rounded corners, we can draw entire strings of characters, and then we can fill in shapes, rectangles, ovals, polygons, and so on. And we can do all kinds of subtler things, like when two lines cross, what should we do? Should we just overwrite the old line with a new one, or should we do something more interesting, like take an exclusive OR of the two pixels colors? There's reasons we would do that if we were talking about animation. So all of this is inside the graphics class. The challenge for us, so this is all background, right? So the challenge for us to actually do some drawing is, how do we use the graphics class? If we just construct a graphics class and we say, you know, graphics object.draw line, it's not going to do anything. It's certainly not going to display something on our desktop or inside a particular dialog that we created in Java. So the theme here is going to be we have to work within a larger system. So there's a system called Swing, which is built on top of AWT, the Abstract Windowing Toolkit, which helps us create frames, okay, those windows with things on the top and clickable options and so on, and buttons and things that we put in frames like that, and typing areas and so on. Swing manages all of that for us. And we can get Swing to do something like draw a rectangle in the middle of our display for us, but we got to know how to talk to it. Okay, so displaying a button, really easy, because I can just click on the button, I can drop it down here, and now when I run this, stuff has happened so that when this frame is displayed, there's a button in the upper left. But how do I get this to draw a rectangle? And I want to use this draw rectangle or fill rectangle method inside graphics. So here's what we're going to do. We're going to use the idea of class extensions. So there's a thing over here called a JPanel. And JPanels are part of Swing. And there's not much to a JPanel. It's got 6 methods, and none of those are particularly interesting to us. But remember, a JPanel is an extension of a component, and a component has a method called paint. And if you look at the paint method, it says invoke by Swing to draw components. And that doesn't really tell us a lot, but the paint method is called with a graphics object. And if we can get a hold of that graphics object that's passed to paint, we can use it to actually do some drawing on our JPanel. So that's all motivation for what's about to come next, which is a little crazy. So we're going to make a new Java class, and I'm going to call it MyPanel. And when I define public class MyPanel, I'm going to say extends JPanel. And it's going to underline JPanel because it doesn't know what that is, but it's also going to say Alt plus Enter. And if I hit Alt plus Enter, it makes an import statement. It says grab classes from java.swing, and that's where JPanel is. So now it knows where a JPanel is. All right, I'm going to put one method in here, public void paint, with an argument of graphics, G. Doesn't have to be called G, usually is. And again, it doesn't like graphics, doesn't know where it comes from, but it does know that it could be from Java AWT graphics, and if I wanted to import from there, I can hit Alt Enter. So I'll hit Alt Enter, it makes that massive import, and now I can talk about my graphics object G. All right, so what am I going to do in here? So let's do G.fillRectangle. And it takes 4 integer arguments, lower left XY position, and then width and height. So I'm going to say G.fillRectangle, and I don't know, let's just put this at 40, 40, and let's make it an 80 by 80 rectangle. It's a nice big rectangle. There's my paint method. So what do I have here? I have a definition of the class MyPanel. And it looks exactly like a JPanel with one difference. The paint method, instead of doing what a JPanel's paint method does, draws a rectangle. Now if I drop a MyPanel into my dialog and I run it, I should get the same type of window, but should have a rectangle in the middle. So let's see if we can make that work. So I'm going to build this as it is right now. I'm going to come back to my main form. Okay, I want to put down a JPanel here, but I want it to be MyPanel. So if I click on JPanel and drag this over, it's just going to be a JPanel. It's not going to use my code. If I want to put my own version on here, I'm going to come over here and I'm going to say non-palette component. So I'm going to left click on that, and then I'm going to drop that right here. And it's going to say, okay, what class do you want this to be? So I can type MyPanel, or I can get a drop-down list. There's MyPanel. So that's what it's going to put in there. Not very obvious, but check this box that says create binding automatically, because sometimes you're going to need this to be bound to a variable, and so that should be a default option. Okay, say OK, and there's our JPanel. It's this tiny little box right here. Alright, so we want this JPanel to be bigger. Remember, there's a window manager in here that's controlling the size and placement of everything for us. So let's short circuit that a little bit. So I'm selecting MyPanel. Remember, there's properties over here. So the two properties I'm going to tweak are horizontal align. I'm going to change that to fill. And vertical align, I'm going to change that to fill. And that's going to make my panel fill up the available space. And you can already see we're going to have some happiness here in a minute. Let's go ahead and run this. There's our window, and if I make it big enough, there's our rectangle.
You could make a checkerboard.
Could make a checkerboard.
Or a chessboard.
Yeah. Or the next great masterpiece.
X and O.
Yeah. I'm thinking I'm not going to do tic-tac-toe for PA3 though.
Oh.
I'm
It's going to be Battleship.
kicking around ideas. Oh, Battleship would be cool. I should do Battleship for PA5 because we're doing networks. I might have you do a calculator for
Calculator
PA3.
sounds simple.
Cool.
Cracking out to do
Yeah. Yeah, that would be cool too. All right, so we're in business now, right? I can come down here to this paint method and I can do whatever I want. I can say G.draw oval, and let's draw an oval at 200, 200, and let's make it 100 wide and 50 high. So it'll be a oval, and we'll run that, and got an oval. So, right, we get all this help from IntelliJ. So if I say set, it will show me all the things that I could possibly set. Set color sounds like a good bet for changing the color of something. So I'm going to say set color. And it needs an argument of type color. Well, let's look at that. So let's look at set color. Set the graphics context current color to the specified color. All subsequent graphic operations using this graphics context, that's G, use the specified color. And the argument is an object of type color, so let's look at the class color. And color has all of these static methods like color.green. That's a static field variable.
There's lowercase and uppercase.
There's lowercase and uppercase. Just because you can. So no difference as far as I know. Probably like a debate that couldn't be settled. So let's set color to color.green. And it knows about the color object because we already imported the necessary libraries. And I'm going to change this to a fill oval so that it's more dramatic. And let's go ahead and run that. And hey, there's our green oval.
It changed the second, not the first.
Yeah, because we set the color after the rectangle got drawn.
So the rectangle is just black, right?
Rectangle is just black because that's the default foreground color. Now we could change that in the properties of the My Panel. We could set what the default foreground color could be. Now let me do something in here that we might be tempted to do. We might be tempted to run some code in here that runs forever and picks up mouse positions and updates the display and so on. So I'm just going to simulate that with an infinite loop while 1 equals 1, just hang out here forever. And let's go ahead and run this. Let me stop the current one. Alright, so let's go ahead and run this. I have not tried this at home, but I have a pretty good idea.
Nothing happens.
So first thing we notice is there's nothing there. Right, it didn't even draw our buttons. And if we had some buttons and we clicked them, nothing would be happening. And this is not what we want to do. Remember, this is event-driven programming, so this is basically an interrupt handler that we're never exiting. And if you don't exit your interrupt handler, all bets are off. So 270 lab, blinking lights, hit the interrupt, you go, and you're supposed to change something, right? If you stay in that loop for 6 seconds, the buttons don't do anything anymore, right? So we do some painting in here and we get out right away and everything works fine. So we don't want to have loops in here. And we'll talk about that more another time. Alright, so this appears to be working, but it's not exactly correct. But it's working anyway. But we've overridden the paint method. We're not actually doing any of the things that the original paint method did. All we're doing is drawing a rectangle and an oval. We're going to want to actually make sure that we also do what the original paint method was doing. And so in the start of this, we're always going to say super.paint G. Call the paint method from the original class JPanel, and then go ahead and do what we're supposed to do for our paint method. And it doesn't look like that changed anything, but sometimes it will. All right, so tomorrow, let's see how we can interact with some of these things that we're drawing. Okay, because we can draw a rectangle. Let's see if we can move it around with the button. So this will take us further into this idea of working within this paint loop. All right, I will see you tomorrow.